this special seminar. It's my distinct honor to introduce our speaker today, Dr. Svetlana Kilina. She is presenting a seminar today in partial fulfillment of applying for a promotion professor this year. So fortunately, we get to see the work that she's been doing over the last several years here. By way of a little bit of background, Dr. Kilina obtained her undergraduate and I believe master's degree at Belarusian State University. Is that correct?
Yes, yes, yes.
And then moved to Washington to obtain a PhD from the University of Washington. And then spent some time at Los Alamos National Laboratory as a postdoctoral fellow there. And found us at NDSU in 2010. Showing the faculty here. She's been what's that? Yes, and to our great fortune. So she was promoted to associate professor in 2016 and has been working in the area of computational chemistry, and she's going to tell you about that today. Just to highlight a few of the things, she's mentored over 10 graduate students, 8 postdoctoral fellows, and a number of undergraduate students in her laboratory. And she has some significant awards. Along the list, I'll just mention a few. She did receive a Department of Energy Early Career Award early in her career. And then in 2014, was named a Sloan Fellow and received a Sloan Fellowship Award. I think the first one in North Dakota, and I think probably still the only one, right? And in 2017, received the James A. Meyer Professorship at NDSU. Her productivity here has been quite excellent. She has, since receiving tenure in 2016, she's published over 55 papers and has several more already submitted. So, with that, I'm going to let her tell you about the work that she's been doing. So, take the floor. It's yours.
Yeah, I guess probably I should start with the title first. Yeah, thank you very much for kind introduction, and sorry for some technical issues which took us about 10 minutes for delay. So in my lab, we're working mainly on, I can put it like organic-inorganic interface, and it includes nanomaterials. We also work with molecular structures such as metal-organic complexes. But for today, I really will be focusing only on nanostructures, and in particular on what's kind of, we call it, there might be a question about should we call it functionalization or not, because in organic chemistry, functionalization means probably slightly different. But the idea is that when we say functionalized nanostructure, it means that we're adding covalently, chemically attached molecular structure to the nanostructure, some little organic inorganic molecules to the surface of the quantum dots, but not phase absorbed, but chemically absorbed, creating a chemical bond. And this is what I mean by saying functionalized nanostructures. And in today's talk, I will be focusing on quantum dots and carbon nanotubes and wherever organic molecules, ligands we can put for whatever reason. So nanostructures by themselves, of course, are very interesting materials because they behave not like bulk structures and not like atoms or molecules. It's really kind of in between. This nano size leads to very interesting quantum phenomena, which makes them to be applicable in, or promising, if not applied already, for variety applications, a huge range of applications, starting from our home consumer products, right, to photovoltaics, and of course, medical, biomedical applications, electronics and biomedical applications as well. But adding some organic parts, organic molecules covalently, chemically attached to the surface provides or extends probably the usability of these materials. For example, it's improved their solubility because it's just rocks, right? Little rocks, including organic ligands will definitely improve solubility. In addition to it, it also usually improves optical properties and also add additional control over photophysics and optical processes in the systems. So the goal of my research or research of my group is to simulate these light-driven processes in nanostructures with complicated surfaces, interfaces, what we call organic-inorganic interfaces, And in particular, we'll be focusing on quantum dots and carbon nanotubes, just because of the time, right? To give the overview of the work which we recently doing for the last 5 years, I'm focusing just on these 2 types of systems. So what exactly we want to understand with our simulations, with our first principle computations, is reconstruction or changes, geometrical, structural changes, which are brought by the surface ligands to the nanostructure. Again, wherever the processes are involved through organic and inorganic interface, it can be charge transfer processes, it can be localization, delocalization of the charge, and also study the local defects, again, due to the attaching small molecules on the surface, or maybe introducing impurities, doping to the nanostructure. And yeah, all these things might also lead to the appearance of the charge or localized charge at some part of the nanostructure, which also will have a strong effect on the electronic and optical properties of these materials, comparing just to the pristine nanostructure. So I will start with carbon nanotubes first, and then move on to the quantum dots. So just a little bit fun. I don't know, is Haley around? Thank you, Haley, for your presentation on Monday, because you gave really nice introduction to the nanotubes and functionalized nanotubes, so I can skip it. But I just want kind of to pay your attention that although we say that nanostructures and nanomaterials are kind of something recent topics, at least for last couple of decades, but people were using nanostructures for centuries. And in particular, the nanotubes example is so-called Damascus steel. So it's known for its being very durable, elastic, sharp, and light, much lighter than regular steel. So these swords or knives are saved, and you can find them, I'm not sure about America, probably also somewhere in America, in Europe, you can find them somewhere in museums. So they have this feature, the surface has a feature like a waterfalling pattern. But it's not only how they look like, it's really their mechanical properties which would distinguish them from regular steel, European known steel of that age. So surprisingly, the technology, or how we call it, the manufacturing procedure was lost. So we don't know how this steel, at least up to a couple years ago, there were some ideas how it was done, but for many years, for many hundreds of years, so the secret of this Damascus steel was lost. And in 2006, there was a research group doing they really take a small piece of the actual Damascus sword and doing this, they're really destroying it by putting acid, hydrochloric acid, kind of washing out layer by layer, one atomic layer by another atomic layer from the steel, from the blade. And at some points they start seeing, and using, of course, whatever the means of, you can do the image of the structure. So I think in this case, they use X-ray spectroscopy and also electron spectroscopy data. So they start seeing really very nice, straight kind of, lines, very untypical, which you usually don't see if you take a regular steel knife, even from the same age. So, and then doing more accurate analysis, they came to the idea that these were carbon nanotubes. They actually were able to see that, the small image on the top, the insert, I don't know, is it hard? Is it probably not very easy to see, but you can see that in these lines, you can see like small dots inside, which showing that there is something also, like this is really tubes. They are empty inside, and some atoms probably were also kind of getting into the tube, inside the tube. So anyway, so they were claiming, using this experiment for proof as that when this steel was prepared, the ore which were used in the area of ancient India, by the way, the mines are now completely gone. They were taken for centuries. So the ore had the transition metals such as chromium, vanadium, some other transition metals, which are well-known catalytic agents for growing carbon nanotubes. So that's why when they were doing this procedure of making steel, carbon nanotubes were also synthesized together and kind of were incorporated into the iron lattice, and this improves the mechanical properties, because we know that carbon nanotubes are known for their great mechanical properties, lightweight, and still will be. We know that the material behaves even even hard. The material is harder than steel by itself. So I just want to use this example to show you that nanoscience was with us for many, many centuries ago already. Well, maybe not science, but we applied this knowledge already somehow. So if we talk, but we interested not in mechanical properties, we interested in electronic and in particular optical properties of these structures. So simple model, just thinking about carbon nanotubes as one-dimensional materials. And I think this is just coming from, you can do this, so you can solve this and get similar pictures if you just take like solid state physics, for example, or we try to give some kind of this exercise in the quantum chemistry classes, higher level classes. So it's a typical one-dimensional so-called Van Hoff singularities, kind of peaks appearing in the valence and conduction band, occupied and unoccupied levels. And the optical transitions are happening in between occupied Van Hoff peak to the unoccupied Van Hoff peak. So at different energies, that's why the spectra, absorption spectra of nanotubes is discrete. And people use like first peak would be E11 from first occupied to first unoccupied Van Hoff singularity, E22 from 2 to 2, right, and so on. This is simplified, of course, picture. In reality, when light is, and this is in the ground state, when light interact with carbon nanotubes, so electron is excited to the unoccupied level, and because carbon is a pretty light material, so its dielectric constant is pretty small comparing to other semiconducting materials. So that's why the coupling between hole and electron, just electrostatic coupling, what we call Coulomb coupling, is much stronger in carbon nanotubes comparing to any other semiconducting materials made from the bottom side of the periodic table. And because of this, so actually there will be creating of excitons. And because of the symmetry of the carbon nanotubes, which is just cylindrical symmetry, so it brings actually twice degenerate, each state will be twice degenerate in this one. Well, there are many states, it's a band, right, with inside Van Hoff singularities. But because of the geometry, it will have twice degenerate states. So which means you can create 4 identical excitons. And only one from this exciton, I mean, identical in terms of energy, but their wave function, of course, would be different depending on the alignment of its transition dipole moment, or alignment of the wave function, direction of the wave function. Only one of this exciton is optically active, and 3 are optically inactive. Again, because of the character of the shape of the wave function for each of these exciton, despite that the energy is very similar. And it turns out that low state, which is optically low state in these systems, is not optically active, it's optically inactive. So actually we have 3 inoptically active states. They're not exactly degenerate because any kind of defects and any kind of interactions will, of course, break this perfect degeneracy, but they are split in a very small energy, like from 10 to 100 millitron volts difference between the splitting between these 4 excitons from E11 band, from E11 optical band. Only one is optically active and it's high in energy, which means low states provides kind of a trapping of the exciton, and emission is quenched at least 3 times, right? Smaller comparing to, let's say, conjugated polymers, where the bright exciton is the lowest exciton. So this explains low efficiency, quantum efficiency for the emission of carbon nanotubes, which is in contrast to many known, other nanostructures usually show improvement in the emission comparing to their parent systems, but nanotubes are not this case because of this dark exciton's position below the bright one. So the question is, what is it possible to do something to improve the emission of nanotubes? How can we kind of switch this alignment and make the low state to be the brightest one? And one of the solutions would be, let's add something to the surface of the nanotube, create so-called defect, because now to add the molecule to the surface to the sp2 hybridized honey ball structure of the nanotube means we need to break this conjugation, this nice sp2 hybridization. So let's do chemically attached molecule, break the conjugation in a local spot, creating sp3 defect or Sp3 bond. And this will, of course, will probably introduce new states, and hopefully they would be optically bright. And yes, they are. I will show it in a moment, and Haley was also discussing it in her Monday talk. So one of the common procedure, by the way, this is very new area of research in general. So the first experimental, computationally, we have done our work in 2012 and published it in Nano Letters, kind of predicting that doing the covalent attachment of aryl ring on a surface provides, well, of course, depending how you put it there, it provides the new state which would be optically bright. And then in 2013, there was experimental evidence showing that, yes, they were able to detect, they were able to functionalize these nanotubes a similar way, and they saw improved of the emission and also much more redshifted emission, showing kind of new state appearing for the nanotube. So they use diazonium salt chemistry, well-known chemistry, I guess they call it a relation, to break this sp2 hybridized bond in the carbon nanotubes and attach and create a new sp3 bond between the molecule and the nanotube. So, and that's why we call this defect sp3 defect. So now in the nanotube, instead of all atoms being sp2 hybridized, a few will be sp3 hybridized when reaction is gone and the molecule is attached into one of the sites. And in this case, of course, you need to have more than one molecule, because if one molecule attached, then we will have a dangling bond, unhappy dangling bond, which also has to be saturated with another species. So it can be the same molecule, or it can be something from a solution, because the reaction is taken in a solution. For our models, we just put in hydrogen. We were also putting OH groups. Technically, wherever the second, the chemical composition of the second auxiliary kind of position ligand on this defect is not really changing the whole story, is not very much changing the properties brought by this sp3 defect. So covalent functionalization. Oh, another thing is, of course, it has to be done in a small concentration, because when concentration of these defects is increasing, if you're not controlling concentration, then defects, then emission is quenched. Actually, you completely quench the emission in nanotubes if you put a lot of defects to the nanotube. So it has to be controlled, and it has to be in a very small concentrations. The concentration right now, they can determine this concentration, something like 1 defect per 10 nanometer size of the tube, and tubes usually can be up to micrometer. So so this defect creates a defect in the lattice of the nanotube, which we call sp3 defect. And now this brings new electronic state to the electronic structure of the pristine tube, and this state is optically active. So here is this paper from 2013 showing, comparing the pristine tube and the aryl functionalized tube with appearance of this new red, right? So red emission peak shifted more to the red, and it's much optically active comparing to the blue peak from the pristine tube. And then it's not only increasing the intensity of the emission for these systems, it's also puts another idea that it's very easy to functionalize the molecules. We can put any kind of groups on a molecule, or we can just change the class of molecules. And we hope this will probably also affect the electronic structure. So we now introduce a new tool for tunability of the energy of the emitting state. Just by regular means of chemistry, which is well known through the engineering, like not really changing the tube or trying to do something with the tube, because it's really very hard to do anything with the tube. It's very rigid structure, but really now playing with the molecules. And another thing is that this defect is even more overall tube emitting in the red/near-infrared range, and the smaller diameter of the tube, backward, the bigger the diameter of the tube you take, the more redshifted energy would be. But now we don't need to worry about the tube. We get in this more redshifted transition, optical active transition. So we really now have the emitting materials in the near-infrared range, which is by itself also very uncommon feature at room temperature to have this properties in the near-infrared range is really not very often presented in other chromophores, well-known chromophores. And in addition to this, it was also found that this emission can be used as just emitting a single photon. So what we call single photon emission. And if we're thinking about quantum applications, quantum computing, quantum informatics, and so on, to manipulate with qubits, we really need, let's say, using light to manipulate with qubits. So we need to have not only coherent light like lasers, but it has to be really just a single photon, right? To emit a single photon for a moment of time. So the second order correlation function, which can be measured or kind of can be interpreted through the measurements showing here. So again, it's telling us that you excite the system and then you probe the system with a delay at the same energy, but with a delay. And if it's a single photon, when it's delayed, if it's a single photon, after some time, you will have no anything on detection, it gives you 0. If it's more than one photon emitted, then this peak in a 0 value will be appearing, will be big and wide if more and more photons are involved. So having nothing or almost nothing around 0 for this J2 function, showing that this is really a single photon. And it's, again, single photon emission is not very rare thing for many materials, but usually it's detected in the low temperatures, in the cryogenic temperatures around 410 kelvins. But at room temperature, this is not very often to see. Another example of such single photon emission is so-called diamonds with the nitrogen vacancies, where nitrogen is substituting carbon in the diamond lattice. So it's also showing single photon emission at room temperature, but it's in the visible range. And it's very hard to change this energy. People trying to do other substitution for nitrogen to some other atoms, but not as successful, not as easy as it can be done with playing with the size of the tube, diameter of the tube, chirality of the tube, and different types of molecules attached to the tube. Definitely provides much easy way for tuning this energy to the not only infrared, but exactly to the what it calls telecom wavelengths, where the signal for telecom connection is already applied, right? For example, around 1500, 1400 is already in the telecom wavelength range. So uniqueness of the electronic structure brought by the Sp3 defect results on new applications, open doors to the new applications of these materials for so-called quantum applications, quantum technology applications. So yeah, it was detected room temperature, near infrared, single photon emission in these systems. But the story is not so simple. So now the defect, although we can control the concentration of defect, it still will have different variations in the position with respect to the crystal lattice of the tube where the defect can be seated. And in particular, so here is we work with collaboration of Los Alamos National Lab. And here is my previous graduate student, Brandon. Many of you probably remember him. So he's now working as a staff member at Los Alamos. And he was starting there as a postdoc working with experimental group from LANL and kind of continue his PhD thesis there. And many papers from 2017 to current on nanotubes with me and him and all other people from Los Alamos National Lab. So were published in the last 5 years. So here we're showing experimental data from Los Alamos group for different tube chirality. And again, chirality, of course, changing the energy of the emission and electronic homolume gaps, the absorption energy. And each of these top panels showing each carbon nanotube sample, means really they do single molecule spectroscopy. And you can see some samples really have just a single peak, some have 2 peaks, rarely 3, usually it's 2 peaks present, sometimes 3. But this peak is like, sometimes it's more redshifted, sometimes it's less redshifted. Around 1000 and this range, it's similar to the regular E11 band of the pristine tube. So it's variety in the energy of this emitting states. And for the 11.0, it also varies, but much less. In other words, if we average over samples, in case of 6.5, we see kind of 3 peaks are present, with the last one blue shifted is corresponding to the pristine nanotube peak. And for the 11.0, it's definitely 2, and it's much brighter and it's much narrow and so on. So it's less difference in the variety of these energies. And of course, the question was why, and this is where computations can really explain, can contribute and explain. So before getting there, just a little bit more details, pretty much repeating what Haley was showing on Monday talk. So position of this Sp3 defect can be in 3 ortho and 3 para, similar as we do this position counting in the same way as in organic chemistry for benzene ring, for example, or any kind of resonance structure. Mass are not stable, so it's 3 ortho and 3 para. Why is it 3? Because it's also orientation of this defect is also different with respect to the axis of the tube. So we need to take it with respect to the axis of the tube. And here's I'm showing 6,5 and 11,0. Tube axis is just parallel, right? You can see that for 11,0, 2 defects are completely symmetric. And for 6,5, all 3 are, 3 ortho defect and the same 3 para. Among 3 ortho, 2 red and green are completely symmetric with respect to the axis for ortho. For para, it would be green and red again, but solid. And for 6,5, all 3 ortho and all 3 para are completely different, right? Because of the chiral vectors, what we call rolling vector for the 6,5 tube is like around 28 degrees. For 11,0, no chirality, just rolled like this without any angle. So also we can think about that from the point of view that this bond formation is coming through the pi electron pi kind of sharing electrons. So for ortho position, there is a more mismatch between pi orbitals, and this angle is more kind of distorted for the pi orbital, which means it's more reactive comparing to the para. So overall, just from this simple chemistry idea, probably general chemistry idea, we expect that ortho should be more reactive rather than the para positions. So now how we do calculations. So for calculations, we work on the finite tubes. We cannot really go to micrometer tubes. We also not applying periodic boundary conditions to mimic the lone nanotube structure. So we play with them in the same way as people do with conjugated polymers. So for computations, so just take several units, maybe 10 units, crystal units in length, put hydrogens at the edges, and work with this big oligomer rather than polymer. So same approach here. But with nanotube, it's more complicated idea what to put on edges, how to saturate the edges, because if you put just hydrogens, it will not work. It's not completely saturate this pi conjugated rings at the edge due to the chirality, especially if it's really rolled kind of with some angle. So I don't have a good theory so far. It was really one of the goals to figure out what exactly would be a kind of a formula for this, how many capping groups, what kind of capping groups we can use. Unfortunately, still empirical knowledge just from computations, putting in addition to hydrogen, so kind of instead of each hydrogen, putting CH2 group, which will provide double bond connection to the edge of the tube, and preserving the aromaticity, the resonance bond structure at the edge with the CH2 group. And then some of the other groups will be with hydrogens. You don't need to have all of them to be CH2 groups. Moreover, if we go in with increasing number of CH2 groups along the circumference of the tube, in this case it was 6,5, you can see that the energy gap, and I'm showing 2 lines, one for quantum, one for semi-empirical calculations, kind of a Hartree-Fock approach, parameterized Hartree-Fock, and one for the DFT calculations. So the gap is getting kind of increasing, opening at some specific case, at some specific number of the groups, of CH2 groups. It's only 2 of them are present, and there are 2 hydrogens between them on the edge. In this case, the gap is opening. Otherwise, the gap is closed because we see the H originated state. So it means like we're not getting the infinitely long, nice structures. It's supposed to be an experiment. So now we know how to make a model, which we can use instead of a big long model, but use a small model, but still will not have effect of these edges to the electronic structure. And yeah, our regular tool, DFT, CD-DFT, linear response CD-DFT to get an excited state and emission state. So first thing which we found out that based on the defect either ortho or para is a total 6, right? So let's consider 3 ortho, and I have 3, and this is electron hole pair contributing to this lowest optical state. Here is the spectra. So and this state for each case is showing here what are the orbitals contributing to this excited state. And again, this is not ground state orbitals, it's excited state orbitals, electron and hole pair. So you can see that exciton is more localized in one cases, in some it's ortho, but let's call it ortho minus, comparing to the in other cases. And technically, if we really kind of plot the localization, the size of the exciton with respect to the energy of this new state, or actually we can also plot it, we call it the redshift, how much this new state, defect-associated state, is split with respect to the pristine E11 band. So this is what we call redshift. So showing that it's almost linear dependence, the more the defect is localized, the more redshifted the defect is, and it's still optically active. The more it is delocalized, the more it is closer and closer to the E11 pristine band. So to go with a direct comparison between experiment and theory, we cannot just take our data and compare with experimental spectra, which I just showing to you, for 2 reasons. Why? One reason, well, DFT functionals, many people know, depending which functional you choose, you can see red shifted, blue shifted peaks comparing to experiment. But this usually it's a consistent shift, means it's you can make a shift of the whole spectra by some constant, and it will be then comparable to experiment. However, in case of nanotube, there's also, we bring this confinement effect because the size of our model is around 10 nanometer size. So confinement effect means increasing, the smaller, the bigger the splitting between levels, according to the, again, quantum mechanics particle in the box model, is there. And because excitons are localized differently for different attachment of the defect, so then their confinement effect will be different. For most localized, the confinement will be felt less, since they don't really feel the end of the system, since they are very localized in the center. For more and more delocalized cases, like pristine one, which is completely delocalized of the entire tube, then of course this confinement will be the biggest. So depending on the defect, confinement effect has a different shift to this defect-associated state. And we try to figure it out what exactly the shift would be, or how to eliminate the shift. So we can really include this as a, maybe not constant, but some parameter, and then we'll compare with experimental data. So here we are increasing the size of the model, going from, well, I'm showing reverse lengths, but we can go with, let's say, 5 units in length, 6 units in length, 10 units in length, 22 units in length, primitive unit cell in length. And see how it goes with, this is our confinement effect, right? The longer the system, the smaller the splitting between levels you expect. So, and you can see that this slope is different. It's the biggest in the case of the pristine tube for the completely confined system when the exciton is completely delocalized, and it becomes shallow and shallow, smaller and smaller when we go to the more and more localized exciton due to the defect. So now we can just take this, the slopes, right, for each of the defect. And now I'm plotting this red shift with respect to the slope. And again, it's kind of almost linear behavior with these parameters, which now I can imply into my energy. In other words, I just need to multiply by this parameter, which I get from this linear dependence, to correct the position of the electronic levels with this method. So here is my formula would be, we take in the energy of the whatever number of units of my system is. So multiply by this alpha parameter, which are getting through this linear curve, and add the experimental data kind of to shift this energy with respect to experimental data. After doing this, I'm showing two different functionals. So with one functional, like the top one, it's exactly raw data as we get in from DFT calculations. Middle, this is when we just do the shift, constant shift, as typically we do to get the arrow due to the, let's say, functional. And the bottom panel where we're using this alpha times, means this parameter which we defined based on the confinement arrow for the Cambis-Philippe functional, and then the same for the Bis-Philippe. So you can see even with Cambis-Philippe, which is a little bit more blue shifted, we get into the range where they see experimental data for these peaks. So now using this method, we really can go with a one-to-one comparison between experimental data and computational data and hope to see good agreement. Let's see. Yeah, so let's see whether, let's apply directly to the 6.5 and 11.0 tube. Now what the middle side panel showing this computational data for ORSA and para. As I already said, the para is supposed to be not as reactive as ORSA, so probably they have much less samples, if none, where the molecule are attached through the para case. And then if you leave in only ORSA, we clearly see that because of the degeneracy, two states, two ORSA, since they have very symmetric kind of alignment, the energy is completely degenerate, which will contribute to this very nice narrow and at least twice bigger peak, the most redshifted one. And in case of 6.5, all three ORSA blue lines will contribute to these peaks, and they are in a good agreement. Well, not perfect, but of course we not expect perfect, because then it would be too much suspicious, right? Since we have so many simplifications and approximations in our model, but in a very good agreement with experiment. And also we can now really explain why the 11.0 tube, which is completely not chiral tube, zigzag tube, has less variations in the emittive species associated with the defect because of the degenerate states which contribute. Well, number of species is the same, but they are not varying in their energy, contributing to this nicely bright transition, twice more intensive transition. So next question is, how can we change or do something with these electronic levels, electronic energies, if we change in the molecule? So this work done by he started as undergraduate student with me, and then he was a master degree student in physics department, still continue working on this project with me. And so we tried to put, in this case, it's aryls and also alkyl groups, fluorinated alkyls and different substituting aryl groups to change their dipole moment, their polarity, and try to see how this redshift, how much this redshifted defect-associated position, whether it's really feeling the dipole moment of the molecule, which is creating this defect. So it looks like when the dipole moment is changing up to 6 dBs, nothing really changing. So we see a big difference with the position, whether it's ORSA plus, ORSA minus, ORSA plus minus, or para, whatever, but almost no change with respect to the type of the molecule. And only when the dipole becomes really stronger than 6, we see a significant change and significant deviation between the different groups. So this is easy to explain, because if you remember, I was showing these localized excitons. They are sitting on the tube. They're not really sitting on the molecule. So it's really defect-associated, tube-associated exciton, which not spread, which not really belong to the molecule itself. That's why the change in the molecule has a very minor effect on the energy of this exciton. Well, there was some experimental data, not our experimental data, some other groups, and not Los Alamos, not our collaborators. So they published this paper recently saying that they're kind of trying to see that if they see defects, 2 defects, or maybe more than 2 defects being placed kind of on a distance around 1 nanometer, so they see variations in this position as well. So like defect-defect interaction is also might be important and might change the whole picture, or at least the energy of this defect. So this is our next step for another story, another paper, which was done by Braden. We now put in 2 defects and want to in a different distance and also in circumference or along the tube to see how the interaction between defect will affect the these levels. So in this case, the idea came that we can use HJ aggregates when you have two chromophores, each of them having dipole, and then there is a dipole-dipole interaction. So if the dipoles are aligned the same way, right, the overall dipole moment is increased, then the optically bright state due to the interaction will be the lowest. If the dipoles go to the opposite direction, and here I'm talking about transition dipoles, optical dipoles. When they go to the opposite directions, and the low state is dark state. So this is a simple JH aggregate model, which just can be derived based on this dipole-dipole interaction model. So we do DFT and then compare with the results of this model to see whether the interaction between these defects can be considered as interaction between two chromophores with dipole moments. So the story was not exactly as simple, because what we saw, first of all, it deviates the behavior of this energy and splitting between this first and second states, bright and dark states. They, of course, not follow exactly the rule of the dipole-dipole interaction, 1 over r cube. So they go with 1.3, I think, or 1.4 power in the denominator, 1 over r with this case. So, but still holding good amount of this dipole-dipole interaction in their mechanism. So moreover, if the defects are very localized, then this model, like they really trapped in two wells, and you can see like, oops, you can see kind of they really, you have two kind of excitons together. So then they really follow much better this J aggregate model. If at least one exciton is localized and another is delocalized, so kind of like one well is shallow, another is deep. So the low state is still bright. Surprisingly, it doesn't follow this backward behavior, but it becomes more and more deviating from the calculations based just on a J aggregate model. So here is the results, and I also show not a longitude, but a long circumference when the interaction is stronger because they're really in a distance of 1 nanometer. So you can see that, and I measure it not in the length, but the angle. So up to some angle, both the DFT calculations and JH aggregate model coincide very nicely. After one angle, after 56 degree angle, JH aggregate model should give us H aggregate instead of J with a dark state as a low state. But DFT calculation showing even after changing this angle, we completely deviate from a JH model, but the low state is bright. So which means that interaction in these cases, in these other conditions, is more deviating from, it's not just so simple as transition dipole moment interaction. But the good thing is that we still have a bright exciton, means interaction between defects will not quench the emission. So if we have two defects, well, not 22, but at least two defects, almost independent at which position and what kind of configurations they would be. Of course, it varies the energy, but the low transition state is optically active. Emission will be seen in this case as well. And I think, I don't know, should I count for 10 minutes, which we were, or should I stop now? No, room taken at 4. Well, I have my conclusion just in case. And then I have a story about quantum dot. Let's see. Let's finish with conclusion and then maybe 5 minutes for the quantum dots. So Sp3 defects break this conjugation in the crystal lattice, creating Sp2 hybridized lattice, creating the localized around defect state, which is usually optically active, but the energy depends on the position of the defect. And the position of the defect controls the energy much more stronger comparing to the change in the type of the molecule which attached to the surface. Oh, and yes, and I don't have actually, I forgot to change the conclusions for the story about Orsa Para, because this was given by Haley. I decided not to show this data. So yeah, so I don't really have these conclusions. So another thing is defect-defect interaction, not completely quench the emission. Actually, it's even sometimes more beneficial because it moves the emitting state more to the red, and the optically dark state is still pretty split out from the lowest bright state, which means emission properties for single photon emission are still preserved, even if we have more than a single defect. And in a short distance, defects, the longer the distance between defects, the more they behave through the mechanisms, through the dipole-dipole mechanism, JH aggregate mechanism. The closer they are to each other, or the shallower the defect is, the more delocalized the defect, then additional type of interactions, for example, like the exchange type of interaction is governing this interaction, and then we see the deviation from the HG aggregate model. Okay, quantum dots. For quantum dots, we shifting the gears not so much on the emission, but we really want to see the processes, photodynamics, photoexcited processes, which are really important for solar cell or actually any kind of energy conversion processes. How does it work? Simple schematics: shining light on the material, creating an electron hole pair, and then it's broken. Oh, you have to break it somehow, and then electron will go to one contact, holes will go to another contact, creating the current. So main properties which are needed to be main steps which have to be done to have this material, any material, to work as a good photovoltaic device or photovoltaic material, is to be able to separate, to break the electron hole pair, separate it, and actually have a charge transfer from one material to another, which then ends up with a current. So for this purpose, the application of quantum dots to the solar cells doesn't, like, you just have quantum dot mix and that's it. So it's much more complicated. Again, goes layer by layer of different size quantum dots, of different type of quantum dots. And here I'm showing, like, for example, cat sulfide quantum dot attached to the titanium dioxide quantum dots, also a few nanometers in size, and then getting to the transparent contacts, electric contacts, but using like glass type contacts to allow light to go through. So excitation is going in this case for the, let's say, cat selenide. We call it the synthesizer because it's excited, and then the electron goes to the titanium dioxide, and hopefully hole will go to some other material. In this case, they use the sulfide ions, polysulfide matrices, I would say, yeah. But there are still a lot of controversial processes which include returning back of the electron which goes to the titanium dioxide. It still can return back to cat sulfide, taking the place of the hole in the cat sulfide, or the hole from titanium dioxide, or it can be also that the hole can be created and again getting to the cat sulfide, which will be actually killing these processes. So there was another suggestion how we can avoid this if we put on the surface of the quantum dot, let's say, some dyes, metal organic dyes, and align the electronic levels to be in a right position with respect to the conduction and valence band. In this case, after excitation of the quantum dot, electron goes to titanium dioxide, and the hole from the quantum dot goes to this dye. And if the coupling is strong, electronic coupling is strong, it goes quickly, pretty much at the same time as the electron goes to titanium dioxide. And now the hole from titanium dioxide will not take the place of the hole on cat selenide, because there's no hole anymore, since hole now is in a dye, and dye is separated with a quantum dot layer. So we suppose this kind of alignment should increase the efficiency for the photo cells, because we're reducing that electron hole recombination, which is of course not a good thing. So far, 14% were observed were in labs with these assignments using this type of materials. So it means still not perfect, still a lot of things have to be understood to control it in a better way. So the same setup of materials can be used for photocatalytic, as a photocatalytic agent. In this case, it would be, we're still exciting the quantum dot, and we still need to have a hole transfer from the dot to the dye. In this case, ruthenium, for example, ruthenium metal organic complexes, they are known to work as oxidizers, maybe not perfect ones, not the best one, but at least they definitely work as an oxidizer, catalytic, photocatalytic oxidizers. And let's say we can use it for the reaction breaking water molecules, right? In particular, oxidation of water side, because the reduction is already known, and catalytic agents for reduction is well established. So another benefit to using quantum dots, because quantum dots are known that it can generate more than a single electron hole pair through one single photon. If it is excited in a high energy, at least twice bigger than the band gap of the quantum dot, we can it can be generated 2 electron hole pairs, maybe 3 electron hole pairs. For this reaction, we need to have 4 electrons, right, to be taken from water to make this reaction happen. So if we can simultaneously create several electron hole pairs, right, of course, it means this reaction will be facilitated much more than it goes step by step, creating 1 electron, then another electron, and then another electron. So this is kind of a motivation why to study these materials. And again, electronic levels of the dye with respect to the quantum dot are very important because they dictate the direction where the hole and where the electron will go, just from thermodynamic conditions. Yeah, so no one wants to go with increasing the energy. So electron will not go to the states which are high in energy. It's much easier to go to the states which are low. So that's why this alignment is very important. And the same for the hole. Well, hole is a backward, because in this case, we can think that electron from the dye takes a place, empty place in the quantum dot. So it's kind of goes from low state to the higher state. So again, with our calculations, we can figure it out what are the conditions which will provide the best alignment for these states. And of course, in this case, it also includes not only electronic degrees of freedom, but also vibrations, since any materials vibrate and there is interaction. When you excite the electron hole pair, it still interact with vibrations with normal modes which are present in the material. Well, very quickly, we do this by taking the bulk system, cut a small size, let's say 1.15, 2 nanometer size, roughly spherical shape structure. Then we can put any kind of molecules we want on the surface, small, bigger ones, do optimization, and then study the excited state. For dynamics, it's a little bit more complicated theory in this case. I probably will skip it since I'm out of time. So first, our observation was that taking cat selenide quantum dots and the, I think it's N1719 dye or whatever, ruthenium dye. So the attachment of the dye to the quantum dot change the electronic levels and the electronic structure of these systems. So first of all, binding energy is also, of course, is the interaction between dye and the quantum dot is also different depending on the position of the dye with respect to the surface of the quantum dot. In particular, we have in the smallest interaction in a case when it is attaching through the isocyanide group instead of carboxylic groups. So, but in addition, the level of the dye, which are mainly coming from the isocyanide, they're also shifting either towards the gap, to the mid gap, if it is attached through the either 1 or 2 carboxylic groups, or shifting towards the inside the quantum dot valence band, kind of not really providing the right conditions for the whole transfer if it is attaching through the isocyanide. So we also calculated the electronic couplings, which kind of corresponds to this processes of electron transfer from the quantum dot when we excited quantum dot to the dye, and then returning back electron from the dye, returning back to the valence band to the hole, taking the place of the hole in the quantum dot. So both rates are presented here. So what we see that the strongest electronic coupling of the electron transfer to the dye is present when we have isocyanide attachment. But it's also providing very strong couplings for the reverse processes, for the recombination processes when electron returns back to the quantum dot, which means in this case, hole transfer is not favorable. Electron transfer probably favorable, but not for a long time, because then because of the strong couplings for the reverse processes, we will lose this charge back to the quantum dot. So which telling us that, yeah, couplings, electronic couplings in case of the attachments to the carboxylic group is much weaker, orders of magnitude weaker, which means electron transfer will not really happen when the molecule is attached through the carboxylic groups. We don't have couplings for holes, but it's gives us the idea that hole transfer should be more efficient. And dynamics, this is our beautiful figures showing actually the dynamics. So what this figures means, it's really three-dimensional figure. So time, the energy, right? So 0 is Fermi energy. So this is valence band, occupied state. This is unoccupied state for the entire system when the dye is there. And then this is just for the dye, like we split and look only levels from the systems which are sitting on a dye, which are localized on a dye. And this is the levels which are sitting on the quantum dot. So the color telling us the population of the state, the more reddish color in a rainbow order. So the more reddish, the bigger the population, the more bluish, the smaller the population of the state. So initially we excite this state, right? This high energy. They belong to the quantum dot. So we really excite the quantum dot. You can see they are pretty much the same state as just quantum dot states. And then when time goes through, this excitation is dissipating to the low energy states of the electrons and holes, kind of getting and end up to the band gap. By the end of the relaxation, there would be on the luma, on the HOMA and on the luma. So, but very quickly, at about 10 femtosecond, we see that electron is not 100% populating, but significantly populating the state on a dye. So although the electronic level splitting is about 0.5 electron volts, so it's really a huge splitting between levels, but it's populating the state pretty quickly. And then it goes with a slow, first of all, we end up on a dye. And then it goes pretty slow with dissipating this energy to the in between the band of the quantum dot states, belonging mainly to the quantum dot states. So overall, we get in its kind of, now we can look on these dynamics. This is initial state losing its population pretty quickly. And then this is the population of the dye state. It goes very quickly, and then it stays at around 30%. And much slower population for the quantum dot population, states of the low energy quantum dot states, which are populating on a range of 100 to 100 femtosecond. So in other words, we have a very ultra fast transfer to the dye, not 100%, but 30%, which exactly what we want, which probably already good enough for applying it to the devices. So I will stop. Well, an explanation for this, it's due to the why the coupling is so strong. The energy is very different, but it has a very strong non-diabatic couplings through the coupling of vibrational mode on the isocyanide with the electronic levels, excited electronic levels, like here. For the HOMA -4, it's a big, because it's spread between quantum dot and the dye. So it's really contributing, this state is electronic level is strongly coupled with this CN stretching. HOMA -2 is showing here, this one. So it's not dye, it's dye orbital sitting on a dye, but it's having a significant portion on the carboxylic group on the attachment. And you can see that because of this, it's already, of course, it also has a coupling with the isocyanide mode. So which means that now electronic, just quantum dot state and the dye state, both are coupled to this dye orbital, and this coupling is strong enough to get it very quickly to the dye. And I will stop here, just showing that the good thing is that we can compare our simulations with data from transit absorption spectroscopy. This is data for completely different system published with our collaborator from University of Texas in Dallas, I think, Professor Robinson. So we working in collaboration with him, and we already published one paper with lead selenide similar to this structure, which I'm showing here, but I will not go to this because I'm already talking for 50 minutes. So, so go to my conclusions. So attachment of the dye to the surface is very important for the electron transfer, or actually hole transfer in this case. And carboxylic group attachment definitely is providing right conditions, thermodynamic conditions for the whole transfer. Plus they have very weak electronic couplings between the excited quantum dot to move the electron to the dye, which means this channel is not really available. So means whole transfer definitely will be possible. And our calculations with dynamics definitely show that ultra fast dynamics is probably feasible for populating 30% of population of the states to the quantum dot. So proving that whole transfer is possible and it's quick. So with this, I will go with my acknowledgement slide of my grants, people working on it, and our collaborators. Thank you very much for listening to me. And I think we probably can have at least 5 minutes for questions.
Thank you. Great seminar. And the floor is open for questions. Yes.
So in your nanotube study, when you're talking about that you have to cap the ends of the tube in a proper way to make the calculations work, but just where you put the defect matter, if the defect is close to the end of the tube.
No, we avoid it. So the defect has to be exactly in the center, to be as far away from the edge. And it's also put some limits on the requirements that we cannot work with the short tubes. Our tubes have to be at least 10 or more nanometer in size. First, to make, well, the smaller the easy. To make calculation work, we can go with 5 nanometer tubes. This would be good enough. But to avoid the interaction between defect and the edges. Because in reality, they probably don't have this case when it's long. It was showing that if defects, well, yes, of course, there are defects at the edges. And if it is not controlled in the right way, then luminescence is quenched. So in other words, what experimental is telling to us is if they see emittive tube, it means the defect sitting not at the edge. Otherwise, it would be not, there will be charge transfer involved, story, which quench emission.
So when you're doing the generation of your disoniums, so it's usually the carbon nanotube which transfers the electron, or can you generate the disonium salt by a totally different process? You get different types of functions. I don't know the literature.
I didn't get like, what's the difference between these two approaches?
Carbon nanotube. You have a disonium. Now, the decomposition of nitrogen from disonium is obviously occurring from the nanotube. Nanotube transfers an electron?
Yes, nanotube is transferring the electron, which create this radical structure.
Right. And what happens if you generate the disonium salt in the presence of carbon nanotube entirely by a different method?
Not use the nanotube to generate it.
My understanding, they just take the salt and add to the tube. And then reaction goes.
Or to generate some other way. I mean, there are many other ways.
Yes.
You can add copper to it.
I'm not sure whether they use metallic or any kind of, well, they probably use some catalytic reactions as well. But like this paper and these examples, it's exactly the molecules which were already probed. So they doing aryls. It's probably, I'm not sure whether it's going through diazonium or not diazonium salt contribution to get aryl attached. Honestly, I don't know. The problem is that when people publish results on nanotubes, in particular, like, you know, this high impact journals, right? Of course, they're not talking about synthesis because synthesis is supposed to be well known. They're not implement new synthesis of nanotubes. That's why if they will talk about synthesis, they will not be able to publish it in Nature Photonics, Nature Chemistry, and so on. So that's why the story about synthesis is completely not there. And they just talk about the characterization of nanotubes based on their optical properties. But yeah, there are different methods how they can do it. And this is exactly new direction of research. As I said, like they start in 2013. It's not enough really time to go through many variations of synthetic procedures here. And not many synthetic people are working there because usually physicists are working on the systems and they have no idea what exactly to do, how to functionalize and how the synthesis should be. So they get in usually the tubes from somewhere, who knows how they were synthesized and so on. Well, I mean, because we having these questions many times to our collaborators, and it looks like it's really hard to get really clear explanation of the mechanism of reactions which take in place, except this diazonium salt, which is well understood. But yeah, it's exactly what they're trying to do now. Switch to a different mechanism of reactions to have a better control of the defects on the surface.
This came up in our daily stuff too. So now your selective functionalization at the ortho position. If you do some electron density computation, you see higher electron density at the ortho position.
You mean,
Just on the nanotube
well,
itself.
first of all, we're not, the question is, we're not doing the reaction. Well, I mean, actually, we do, actually, Dmitry is doing. So right now, for the things which I didn't show, we try now to simulate the actual reaction, try to simulate how the reaction is taken. But we actually look just on the product when it's already finished. So, and then, but if you're asking what exactly the electronic orbitals look like, this is how they look like. So they vary between different Orsa. And of course, they vary between para as well, but I would say like those most red shifted, either para or Orsa, they becoming very localized, means your charge density, yes, is increasing around the defect, but it's not because Orsa or para, it's mainly because of the geometrical position with respect to the axis of the tube.
So before the reaction, on the nanotube itself, before you actually form the
Be-
bond, do you have a higher electron density in those ortho positions? That's the
We-
question, I think.
But that's why I say I cannot answer this, because we're not doing simulations of the transition state. Dmitry does.
Yeah, because it could be, might not be important because it could be polarized.
Yes, and another thing is because exciton density or electron density is very delicatized.
In terms of what you see outcome, you see the higher amount of functionalization. And then the higher
Well, we're looking on the charge density, I mean, like really charges on each carbon. So again, the charge very sensitive, well, change in the charge is very small, but this change with respect to pristine tube, right? We're talking about change in a carbon with respect to pristine tube, showing that you have a bigger change in the Orsa position rather than para, which also showing that it should be more reactive. Yeah. So it's kind of indirect, an indirect method for checking that, yeah, what we think about this mismatch between pi orbitals, increased charged difference in case of Orsa, kind of indirect signatures that it has to be more reactive.
Because in a global sense, maybe you can't identify. In a local sense,
So you're saying that, let's say, if you do the reaction with nanotube, you will be able to get just Orsa in specific position with respect to axis of the tube, just a single configuration. Is it possible?
so when they actually functionalize, different functionalized nanotubes, how do they do? How do they do the reaction?
Well, for the isonium salt, yes. For other type of reactions, I don't know. But again, for the isonium salt, they see electron transfer happening first very quickly, and then they even see the formation of N2 gas. So that, and then it goes with attachment of aryl to the surface. Yeah, but I would be happy to discuss it with you. and maybe we can get some collaboration.
They functionalize carbene is take care of isonium salt, but I think the carbene, yeah.
Yeah, but it looks like these are both going through the RCAT.
Yeah.
So, I can't see the chat. Is there some
Oh,
questions in the chat?
actually, yeah, because we,
There are two questions from chat. I can read.
That's fine.
would you please read? Yeah,
Yes.
because I don't see it.
So, question from Professor Asula from Polymers and Coatings. Thanks for interesting talk. Can you give a couple of examples the type of organic molecules attached to carbon nanotubes that give the largest red shift in your calculations?
Well, I guess, yes. So among these, how many? 15 different type of molecules, right? So if we take in the position of Orsa, which is the most redshifted, this would be the squares, right? mainly. Well, there are some after big one, there are some also deviations with these triangles, but squares corresponds to the O+ configuration, right? And they're showing the biggest difference between pristine energy E11 and the defect associated state. So you clearly see that, yeah, well, a little bit like a few millielectron volts, tens of millielectron volts difference will go towards the cases when molecule having a stronger dipole moment, right? So for example, fluorinated cases of alkyls and so on. If we have in two, here we have one molecule and one hydrogen creating one defect. When we have an identical strongly molecules with a strong dipole moments, of course, the interaction is increasing, they kind of repel each other. And this has even stronger effect and more redshifted cases for the two fluorinated alkyls chains, lone alkyl chains, well, C6 at least, right? Or two fluorines sitting together. So then we see the most redshifted transitions. But again, change in the redshift with respect to the molecule goes tens of millielectron volt difference, while the position gives us hundreds of millielectron volt difference from 0.3 up to 0.005, right? Electron volts. So we have orders of magnitude difference between these shifts, and very teeny change if we change in the molecule, at least so far what we see. It's right now we're working on a divalent attachment of the actually dipyrene. And also with hydrogen. So we're thinking that it has to be attached through the, like both these ones. And if there are hydrogens, probably it should be then attached even through these sides. So but this is what we're trying to do now. And we already see that behavior, well, at least the trends which we saw before with aryl functionalization now is different for this molecule. I cannot say whether it's more redshifted or less redshifted, but definitely there is not only qualitative, but not only quantitative, but really qualitative change between when we go to the completely different molecule. And different attachments through the one molecule through the, just one molecule creating this Sp3 defect, except in contrast to two molecules making Sp3 defect. What was the second question?
Yeah, there was a second question from Nick Erickson, a student in polymers and coatings. Can you describe what is happening and what is the purpose of the heat map figures?
Heat map figures. What is a heat map figures?
Maybe he can type, but I assume he means the
this one
distribution in the quantum dots.
Oh, is it nanotubes or quantum dots?
Author of the second question has here. Tell if you.
But initially the question was about what?
What is the purpose of the heat map figures?
Heat map figures.
I think
probably it's for the quantum dots. This one's. Well, this figure is showing dynamics, really not just static picture. Okay, you shine light and then you see the spectra. It's showing how after excitation, what's happening with this excitation. So you start with like again, this is energy. So you start with the energy. I know for Zoom, they don't see me on a Zoom probably when I show, oh, they do. Okay, so we start with the quantum dot states because we know that they're coming from the quantum dot states initially at the initial moment of time. Time is here, right? So then when time passes through, this excitation goes down to HOMA-LUMA states, right? So populating more and more states are kind of getting to the close to HOMA and close to LUMA. So, and if we hold these dynamics for, I don't know, nanoseconds, then of course we will completely have everything, we will end up at the HOMA-LUMA level, right? So it's given us the idea how exactly this excitation is dissipating, is moving to another electronic states. And this move to another electronic states is happening through losing its energy to vibrations, to the heating the system. And yeah, I would expect that this state, dye state, which is very splitted from the main band of the quantum dot, should be populated probably around 1,000 femtosecond, right? Picosecond range because of the big energy difference. But surprisingly, it is populated just after 10 femtosecond, very, very quickly, because of the very strong non-adiabatic couplings through this high energy band CN stretching in the isocyanide group. And the electronic levels is also sitting on this kind of connected through this isocyanide group. Yeah. This? Two carboxylic group versus one carboxylic group. With the arrow? Yeah, so this projected density of states, which means colors of the peaks. Well, black one is a total for the entire system, and different colors contribute to the states, which are mainly localized either on ruthenium blue, on the isocyanide ligand, orange, bipyridine ligands, cyan, right? Green is carboxylic group, and the quantum dot is dashed red. So which means since there is no red, and there is mainly orange and a little bit of red and cyan color, this is a dye state, mainly localized on the either, I don't know which one, probably on both, which is localized somewhere on this part of the molecule, right? And it's this state of the dye is contributing to the already sitting kind of in the gap of the quantum dot, red dashed lines. This is the gap of the quantum dot, so the dye states are inside the gap of the quantum dot. So what exactly was your question? The reason for what? It is exactly the trap state, but this is exactly what we want. We want to trap hole to this state. We excite the quantum dot, right? And then we want electron from the quantum dot, which we excite somewhere here, right? Hole is somewhere here, electron is somewhere here. Electron will be taken to the lab or somewhere there, right? To titanium dioxide surface or somewhere. We're not included here. But we want that the hole, not sitting on quantum dot, we want it to be moving to the dye. And then will be trapped on the dye. And then from the dye, it goes to the solution, discharging through the regular kind of processes with the solution. Or with, with whatever surrounding environment you have around this system. Yeah, does make sense? So you're absolutely right. It's making a trap state, and it's exactly what we wanted. We want to have a whole trap state, but we want to control this step to be originated just from the dye, to sit on the dye, not on something else. Not sure which one you're talking about.
The slide of ortho defects versus para and the misalignment of orbitals results in ortho.
This one?
Yeah. So it's been a little bit since I read that paper, but from what I understood, the orbital misalignment showed that like it showed one or two of the ortho positions being more favorable than other.
No. It's showing difference, misalignment between para versus ortho mainly. So the para will have less misalignment and ortho will have more. And of course, each ortho also probably not identical to each other. But in average, any ortho will be more misaligned of these pi orbitals with respect to para. So this is the logic saying that ortho is supposed to be more reactive.
I guess I get that from this figure. It more looks like it's showing the alignment between the ortho positions.
Yeah, here it's showing, yeah, both are kind of showing the ortho, right? I agree. Well, I guess I guess this picture probably not very representative. You really need to look on the structure of the nanotube. And then I think you will see that if you look in on this and this, right? So here it would be more kind of out, and this will be more like perpendicular. So you will see a difference between these angles for identical para and ortho. Yeah, maybe this picture will show you a little bit better. I'm not sure. Like, doesn't matter which, whether it's not 11-0, whether it is, this is 11-0, this is 6-5, right? So kind of this ortho, right? They will, each of this ortho will give you this 17 angle misalignment. And if you look on the para, it will not. So the angles which having the biggest misalignment are marked with red, in other words. And it doesn't depend on chirality, it just depends whether it's ortho or para. Something like this. But again, there's no really rigorous measurements of some value. Like we not really measure the p orbital, whatever angle. It's not a measurement, it's just kind of overall structural idea about how the orbital should be aligned with respect to the surface.
All right. Any last questions? Not, let's thank Dr. Kilina again.
So we're done. Thank you very much. Have a nice day.